Okay, so all right, so yeah, so we're recording, and as a way to, like I said, go back, review, reinforce. Go back. You can pause the video. You can take really good notes, so you don't have to worry about getting everything in your notes in class. You can really pay attention in class and follow along what's going on. So, there's so many things going on in your life, and you can walk out of here and think, yeah, that made total sense. 90% of that, I got it, I'm good, right? But then 3 hours later, 6 hours later, 12 hours later, it's fading. It's the first time you ever saw it, right? That's what the video's for. Go back and watch it that night or the next day and take good notes, and this is where we're going to reinforce and really learn it, not just understand it the first time, okay? So let's just talk about your homework. So this one right here, this function, a of x, or a sub h of x, equals negative 0.75 times x minus 6. Where did that come from, right? Where did that come from? So, and I mentioned it was probably maybe the most important thing of the first class, right? Maybe the most important thing of that first class was where we got that function from. And what was it? Remember? Yeah.
It was dy is equal to m dx.
That's it. dy equals m dx. And in this case, dy is a change in height, right? A change in height, but then starting from 0.6 seconds, right? So this is a change in height starting from 0.6 seconds. Our rate of change of height was the negative 0.75. Height is positive up. So a negative rate of change means it's decreasing, right? The height is decreasing. And then our dx, x minus 0.6. Final value of time minus initial value of time, because it's our dx, right? So that is the way that we frame constant rate of change, right? Constant rate of change, this value of m. This equation tells us what that m means. This equation tells us what that m means. It means not just given a change of 1, but given any change of our independent, in this case time, given any change of our independent, that rate tells us what our change in height is, right? So given that half a second went by, or 2 seconds went by, or 4 seconds went by, change in time, the constant rate then immediately tells us now what that corresponding change in height was. Okay? So that's where we get this net accumulation function, right? Net accumulation function, the accumulation of height of the flag starting from 0.6 seconds. All right, so let's look at these graphs down here. So we have this graph over here, and I think I asked you to, explain the meaning of the points. So here's the point 1, negative 0.75. And so what is the meaning of that point? What does that point mean as you're looking at that? What's the representation of? Any volunteers? Yes, sir?
The rate of change 1 second after the flag is dropped is negative 0.75.
Well said. He said the rate of change 1 second. So this point is that at 1 second, the rate of change is negative 0.75. That's what that point means. Likewise, this point over here is the point, 2.3, negative 0.75? That point is what? It's the correspondence of our two quantities at a particular value of time, right? It's when 2.3 seconds has gone by, the rate of change is negative 0.75. Okay, so that being said, what is this red line? When you draw this red line, what is it really representing? What is that? Yeah. Okay, is the red line the rate of change? Is that what the red line is? It has to do with it, but the line itself, this graph, is not the rate of change.
It's saying that the rate of change, the rate of change is constant as time progresses.
That's what it says, but what is it? So the question I'm asking you really could be the question about any graph, all right? When you look at a graph, what are you looking at? Doesn't have to be a function. What someone said, started saying, yeah. It's an infinite set of points, right? When you see a graph, any graph, what you're looking at is a bunch of points, a lot of points. It's just it takes too long to draw it that way. See? Oh my gosh, when's it gonna end, right? It's just much easier to go, there's our points. So when you look at that, that's what you have to think, right? When you look at a graph, you have to think, oh, that's a bunch of points, and each point is telling me the correspondence of these two quantities, right? A particular x matching up with a particular y, whatever those quantities mean. Okay, so really important. It's not a stick, right? It's not a stick. It's a bunch of points. It just takes too long to draw it that way. If we could, we would. If it was quick, that's how we would draw it, so that we're really thinking about what it represents. Okay, over here. So this is the point. What? So yeah, what is this? 0.8? 0.8? And is it negative 1.5? Or negative 0.15? Negative 0.15. All right, so I want you to get a partner, talk to the person next to you for about 20 seconds, 30 seconds. What exactly does that point mean in the context of the situation? What's the meaning of that point? 0.8 comma negative 0.15. Make a friend. Everyone make a friend. Everyone's talking to somebody. Explain what that means. Go. Someone in the back. Volunteer. Someone in the back. Nice and loud. What do you think the point 0.8 negative 0.15 means? Any volunteers? Yes, please.
Net accumulated change from 0.6 to 0.8 is negative 0.15.
Okay, so he said the net accumulated change of what?
Okay.
Change of what?
Height.
Change in height. He said the net accumulated change in height from, this is the key, starting from 0.6 seconds to 0.8 seconds, and this way, is negative 0.15 what? Meters, right? So starting from 0.6 seconds until 0.8 seconds, the flag went down 0.15 meters. That's what that point is saying. That's the meaning. That's what this net accumulation function is all about. We just chose to start from 0.6 seconds. And so then this function is going to tell us how much the flag went down at any given time since 0.6 seconds, with the total amount that it's, or the net accumulated change. Is that what you said when you talked? There's a lot there, and all those details are important. Okay, so it's just not, oh, it's meters, right? It's the height of the flag. No, you got to have all the details. Any questions on that? All right, so real fast, I want to. So you might have to raise your hand and say, Mark, I have a question, because it's a little hard to see you guys. All right. By the way, I'm Mark. You can call me Mark, all right? So I'm your Calc 2 instructor, and feel free to call me Mark. And I'm going to be learning your names very soon. Okay. So real fast, so you're going to be, you've downloaded Graphing Calculator. If you haven't yet, you should today, okay? And so this is going to be a key element in the course. It's a really great way to learn, because we're not putting in a computer language, it's not learning a new computer language. It's just you enter the mathematics. And when you enter the mathematics, it does exactly what you tell it to, okay? And so we want to be precise in our mathematics, and you'll find out if you miss something when you type, make one wrong keystroke, or you make a little error, well, if the math isn't right, then it won't give you what you want, okay? So let's talk about functions. So we want to define this function. I'll do capital A. This is just kind of extra. You don't have to do this, but Control L gives you a subscript. And so now we want to define a function. So we don't want to do Shift 9, because Shift 9, just putting parentheses, will give like multiplication. So I'm going to do Control 9. And that right there is what we call function notation. Does that whole thing right there, is that the value of an independent variable or the dependent variable? Dependent, right? It's on a graph, it's like the vertical, the y value when we graph. Okay? So that's called function notation. Function notation is going to be huge in this class. Okay, we're going to be talking about it and using it all the time. So we said negative 0.75. This side over here on the right is called the rule. The rule is what takes the value of the independent variable, which is x, and tells us what the corresponding value of the dependent variable is. All right, but therefore that's equal to what the value of the dependent variable is. So we got that. And so I want to graph this. All right, so this doesn't graph it. This just defines the function. The graph is just one aspect of a function. It's just one way to represent it. Okay, they're not one and the same. So it's a very common way we're going to represent functions, but just defining the function means defining the relationship between, in this case, time and change in height, but it doesn't graph it. So for GC, the prompt to graph is using x and y. So if I say y equals, now it's going to know, oh, you want me to graph this. You want me to display this. So what does y equal if we want to graph? Y equals what? X? A sub h of x, right? We said function notation, this function notation. All right, and don't use shift 9, use control 9. Control 9 is what makes the function notation, and so it's not multiplication. And so now it knows, you want it, so now it's saying you want to put the independent variable on the x-axis, and you want to show the dependent variable on the y. Okay, I'll do it. That's what GC says. So there it is. Now, but we only really care about seeing this starting from where? 0.6, right? So I'm going to do comma x greater than 0.6, and now it's just going to show that part of it. And so now this is looking a lot like that graph that we had, okay? The graph that I showed you. Now, say we want to highlight that. Let's highlight that point that we talked about. So to do a point, you do control 2. Control 2 gives you this kind of vertical point here. And so it was at what time value? 0.8. Okay, now suppose I did I want 0.815. Do I have to take that 0.815 and figure out what the y value is to put it here? What can I do instead? Yeah, right. So this is the beauty of function notation. We already defined the function. It knows what every y value is for every x value because of how we defined it. So now I can just write a sub h of 0.815. That is the y value, the value of the change in height corresponding to the 0.815 seconds. And it will do that for you. It'll come back here and it'll reference this and it'll do it. And so there in blue, right? So you can change the colors of stuff, but in blue it highlighted that point. Did we add a point to this graph? Just highlighted what was already there. We know that's all points, right? We know that's all points. Okay? Or I can just come, what if I want to know what that value is? Well, I can just come in here and do a sub h, capital, sub h of 0.815. And now it's telling me what that value is, right? So that's just giving me the actual value, which I could have put in my point too. I could have put negative 0.16125 in the previous line, and it would give me that point. So that's just some real basic things. This is things we'll be doing a lot. Graphing functions, graphing points, using function notation to get values, right? Using function notation to get values, and GC does it all for you, okay? But you got to have the math right? If I type something wrong in one of those lines, it's not going to do it what you intend it to do. Math is a precise language, so it forces you to be precise as well. Okay, can we walk around and make sure people are, if they're on computers, they're taking notes, right? You can use your laptop to take notes, but that's it, okay? No Facebook, and so I got my police men are coming here. All right, same with phones. Thank you. Okay, any quick questions about GC? So that was just a crash course on the most common things that we'll do, but we'll do some more than that. Any questions on that? Please.
What was the command for the parentheses?
For function notation, you need control 9. If you just want to use parentheses to multiply, then shift 9, just normal parentheses. But control, if you're doing the function notation like I did here to set up the function, graph it, you need control 9 gives you the function type parentheses. so that it knows you don't want to multiply, but use function notation. All right, other questions?
Yeah, excuse me.
Yeah, please.
How did you do the points again?
This to the point. Control 2. Control 2. To start a new line, you do control enter, control return. Control 2 gives you a fresh new point. So then you just fill in the blanks, fill in the X, fill in the Y. Other questions? Yeah, so if you're doing GC in class on your laptop or taking notes, that's great. But just as long as you're engaged, okay? All right, so here we go. So we were on this journey of, that homework was reviewing class, which is this journey of, we know how fast a quantity is changing at every moment. We want to know how much of it we have at every moment. That's half of calculus. That's half of calculus, okay? Maybe you were unaware of that when you took Calc 1, but now we're gonna be aware of that, okay? So let's keep going on that journey here. That's the wrong one. This one, where is it? There it is. Okay, so this is we're kind of doing kind of like a crash course from Calc 1. We're gonna do this first week. You know how fast the quantity is changing every moment. You want to know how much of it you have at every moment. Principle 0 was variables vary, right? Variables vary. Principle 1 was constant rate of change, right? Constant rate of change, which we understand by dy equals mdx. dy equals mdx, okay? So principle 3 is changing rate of change. So the same soldier, maybe this is a different soldier, lowers American flag from the top of the pole according to this rate profile now. So I want you to take 30 seconds. So this is rate of change, but it's a different rate of change graph. Okay, different rate of change graph, different set of points. Okay, I want you to talk to your friend again and say, why does this rate of change profile kind of makes more sense than the first one that we looked at? Why does this one make more sense than the first one? Go.
Like that's why there's like constant rate.
He's actually
And then the parts where it's 0, that's just like that's where it's taking nothing. Yeah, something like that.
Okay, they got it in the front row here. I heard them. They got it. Great. So how about this area over here? What did you guys say? Yes, please.
the person lowering the flag
Uh-huh.
most likely not going to stay at the same rate of change the whole time. They might get a big hole and then stop.
Right.
And they'll keep going.
Why would they need to stop? So they give it a big pull, and then why do they stop? Switch hands, right? So there's this, you pull down, that's the kind of this constant rate from before, and then there's kind of this pause, maybe slows down, there's this pause, and then reach with the other hand, and then the next pull, right? So this is now we're talking about changing hands, and in between hands, the flag's gonna slow down and maybe just for a moment not be moving. So that's what we're looking at there. Okay, so what I want you to do is I want you to sketch so the same net accumulation function, the one starting from 0.6 seconds, just real fast. What would it look like now? What would the sketch of the net accumulation function starting from 0.6 seconds look like now? So sketch that. Let's move. Just want to make sure I don't give it away here by going to the next thing. There we go. Okay. All right. I don't want to power off. Really? You can't just mute it for a second? That's really bad. The video projector will be muted for 15 minutes before powering on. Oh, wait. There we go. The notice went away. I'm glad. Okay, go. So you're sketching the new net accumulation function, still starting from 0.6 seconds. How will it be different now? What will that look like? Remember our net, what was our net accumulation function before, right? So now what will it be now? So this is the same. Yeah. Compare with the person next to you. So take about 30 more seconds. Compare with your new friend.
Right. I have to stop it just a little bit because that's the part where he's walking.
So in between hands, does the net accumulation function go up a little bit? What does it do? Levels off, right? So there's no change. So it's gonna, in between hands, it's gonna level off. So did you have something like that? That's what you should have had. Okay. So this is this. So here, this is kind of the journey we're on here. You know how fast the quantity you have at every moment. What? That's the rate of change function, right? At any moment, meaning at any time, you know how fast the height is changing. That's what that graph represents. That function of rate of change is a function of time. You want to know how much you have at every moment. So if we're thinking about height, well, that's like so close to what we're talking about here, change in height, right? So change in height and actual height of the flag are almost the same. It's like a real simple transition between those two. So how much we have at every moment, it's fair to say this change in height is telling us that, right? Okay, so, but now we have a changing rate of change. So when we had the constant rate of change, that, how much we have at every moment, that accumulation function was easy, right? It's a linear function. Okay, but what about now? So this is not easy anymore, right? This is not easy anymore because the rate is continually changing. As soon as a little more time goes by, you have a different rate. And that dy equals m dx, that depends on m staying constant for whatever your change in x is. Okay? So, how do we write the net accumulation function when the rate of change is changing? This is the big question. This is the hard question. Right? So, when you have constant rate of change, piece of cake, linear function, right? Linear function. When you have changing rate, how are we gonna develop that function? So this is where the real challenge comes in to this. You know how fast the quantity is changing every moment. You want to know how much of it you have at every moment. Okay, so let's talk about it. So what do we do? So here's what we do. Here's our rate of change function. I'm gonna slice up time into what I'm doing there. Starting from 6, looks like I'm doing 0.35 second time intervals. And who remembers, do you remember from Calc 1, what am I going to do, or what would we need to do, right? So we know how to get a change if we have a constant rate of change, right? We know how to get a change in height with a constant rate of change. So in each of these time intervals, I'm going to try to mimic the actual rate function with one single rate, one constant rate. Then we can do what we did before, dy equals m dx. This is the key, right? So I've got a changing rate. So I need to try to come up with a function that simulates this one, but does it with constant rates. And then we can use the math that we learned in principles 1 and 2. And 3, I think. Have we done 3? Yeah. Okay, so this is delta x of 0.35. That's a set fixed change in x, 0.35 seconds starting from 0.6. And so in that first interval, what constant rate would mimic or try to reproduce the actual rate of change? Are you going to put it at negative 0.5, negative 0.1? Where are you going to put that first rate? That's an easy question. So in the first interval starting at 0.6, what constant rate will do a good job of mimicking this blue rate function? Negative 0.75, okay? So I'm going to draw that this red bar is showing that here's a constant rate that is the best we can do, in this case really good, right? of mimicking that blue function. So now the next interval is not so easy, right? So the next interval, it's like what one constant rate will mimic that changing rate. So I just need to do one. 0? Does 0 kind of encapsulate? Maybe is that one rate that encapsulates that whole thing? It starts down here at negative 0.75, goes up to 0, and then comes back down to negative 0.75. So what one rate kind of does the best that we can do to mimic that? It's kind of like something in the middle, right? It's kind of like we were trying to like average all these rates together, like the middle one. So I just said, and someone else might say something different, but I said negative 0.4. So do you see what I'm doing? I'm creating a new function out of constant rates that's trying to be like the blue one. That's the best that we can do, right? So I only get one rate in that second interval, so I'm going to say negative 0.4 is kind of like the best I can do to mimic that wildly changing rate. Okay, what about in the next interval? What should I pick for the next interval? What? No, look where the rate of change is. The rate of change is like this, right? Yeah, so again, we can use negative 0.75 again, because that's basically what the rate is there. All right, you might make it a little higher because you have some rates that are slightly higher there, but this is just eyeballing. Okay, what about the next one? So the next one, we see all the rates from negative 0.75 to 0, but then at the beginning, there's this part where it's basically negative 0.75. So what I want to go make it more or less negative than 0.4? More negative or less negative? More negative, because I have this part down here that's kind of would like pull the average down, if you want to think of it that way. So I said negative 0.5 for this one. And when you're doing this, you could come up with slightly different values. But you wouldn't want to say 0 or negative 0.1 for this. Okay, next one. Now this one it's basically 0 to negative 0.75, but has more of a range, more of an interval where it's negative 0.75. So more or less negative than negative 0.5. This next one. Even more negative. Do you see that? Because more of the interval is down here at this negative 0.75 rate. So I said negative 0.6 for this one. This next one is kind of the mirror image of the previous, so negative 0.6 again. And then this one is like the mirror image of this one back here. So I said negative 0.5 again. So do you understand what I did with this red? I'm making a new function, this red one, that's trying to be the blue one, but with constant rates every 0.35 seconds. Does that make sense? And if you would have made this, you would have had slightly different, it should have been close to those numbers, but maybe slightly different, okay? Because we're eyeballing, right? We're just like eyeballing our best guess. Okay, so this in the last interval, negative 0.75. So this is the idea of this principle 4. Pretend rate function. It's pretending to be the real rate function. Right? It's this red function now is pretending to be like the real one, the blue one. But, right, we just made this blue function worse though, right? This is not accurate anymore. Why did we do that? If we had the real rate function, why did we do that? Why did we make it worse? Huge question, right? Why did I just chop it up and create this red function that's like now, it's like approximate. It's not as good. Why did I do that? Yeah. Right, because now I can use the math dy equals mdx, and I can actually calculate some changes in y now using the red one. And then that accumulation function will be approximate to the accumulation function that we're after, the one you sketched, right? The one with the pauses. Okay, so we're going to do that numerically here. So I have time elapsed at the end of all the intervals, 0.6, 0.95, etc. Then I have a column for approximate rate of change, approximate change in height, and then approximate net accumulation of height. And your goal is to fill in this table. Right, but before you fill in the table, I've got some questions for you to think about and guide you through it. Don't start yet. I'll just talk through it, and then I'm going to take attendance. Why are the columns in the table staggered, offset in the way that they are? You want to talk and understand, why did I stagger the table, those middle two columns? Okay, next question. What key concept will allow for computing the approximate height in each interval? Meaning this is asking about this third column. How will we be able to compute approximate changes in height in this column right here? And then the last question is, now you're ready to fill in the table. So make sure you answer questions 1 and 2, understand, and then proceed to work on filling in the table. Okay? So you work with your new friend, work with your friend, make a new friend, work in a group of 3, whatever. But everyone's engaged. You're either making progress or you're getting help, all right? You're either making progress on this, getting help. But talk through questions 1 and 2 first. Make sure you understand questions 1 and 2 before doing any calculations. Go. Oh, we got to move fast. Okay, why are the columns offset? So what is it about approximate rate and approximate change in height that I want to put the columns the way I did? You should have said, because those are values that are true over an interval, right? So this value is true, corresponds to, is associated with this interval from 0.6 to 0.95, and say this value right here is the approximate change in height that you get for this interval of change in time. So the staggering should make sense. Does it make sense? Okay? But then the net accumulation of height, that corresponds to particular values of time since 0.6, right? So then we're back to, so this value right here will be what? How much the height has changed at 1.65 seconds since 0.6 seconds, right? So the staggering should make sense the way that table is built. Okay, so we're going to fill in the empty columns. So how am I going to get the approximate rate of change? This second column here in the table, where do those come from? How do we get those? The ones that we picked, right? We eyeballed, right? Those are the constant rates in red. So it'll just be those values. Did I do them one at a time? No, I did them all. Okay, and then how am I going to get the approximate changes in height for each, so this is for each interval, right? So, did I get red? I got red. So this was, say, negative 0.75, red, and then negative 0.4. So here we are, negative 0.4. How am I going to get the approximate change in height for this interval from 0.95 to 1.3? Where does that come from? You're saying times it by 0.35? Yeah. So this is our dy, right? This right here is exactly dy, approximate change in height for an interval, and my interval length of time is dx. So these are my mdx's, right? mdx, where the m is the constant rate that I had from that interval. Are we good? Now, how am I going to get, so tell me some of these here. Back to black. So tell me, let's do a couple here. Quick.
Negative 0.2625.
263. Someone else get that? Okay, next is?
Negative
1.4. One more. 1.75. Is that right? You got that too?
Yes,
Back to this first one again. So you should have gotten like that. So now how am I going to build a net accumulation function, right? So in the first interval, our height changed by this much, and we started at 0 change in height. So now what's our net accumulation of height?
It's negative 0.265, or
263, 2625. Okay, now what about, now what's my net accumulation of height after 1.3? What am I going to do? You have the accumulation from before, and you're going to add on the new accumulation to get the net accumulation all the way back to 0.6 seconds. So what do we get? Negative 0.4025. So what accumulation means, you're accumulating, right? You're adding on the new change to all the change that from before. That's accumulation, right? So in this column, we're adding on all the new amount of change to all the change that we had before. So you can just glance at the values here. And see if it agrees with what the table you came up with. And then one last point here, so then what is this? If I put together time elapsed and approximate net accumulation, I have some sort of net accumulation function, right? Points, correspondence points of time and net accumulation. And that's what we were after. But is it the exact net accumulation function? No, because it was based on this red approximate rate function. So this is an approximate net accumulation function. And we'll pick it up there next time. Look on Blackboard for class video and any homework that may be due Friday.